Customer Information Control System is a transaction server that runs primarily on IBM mainframe systems under ZOS and ZVSE. CICS is middleware designed to support rapid, high-volume online transaction processing. A CICS transaction is a unit of processing initiated by a single request that may affect one or more objects. This processing is usually interactive, but background transactions are possible. CICS provides services that extend or replace the functions of the operating system and are more efficient than the generalized services in the operating system and simpler for programmers to use, particularly with respect to communication with diverse terminal devices. Applications developed for CICS may be written in a variety of programming languages and use CICS applied language extensions to interact with resources such as files, database connections, terminals, or to invoke functions such as web services. CICS manages the entire transaction such that if for any reason a part of the transaction fails, all recoverable changes can be backed out. While CICS has its highest profile among financial institutions such as banks and insurance companies, over 90% of Fortune 500 companies are reported to run CICS along with many government entities. CICS is also widely used by many smaller organizations. CICS is used in bank teller applications, ATM systems, industrial production control systems, insurance applications, and many other types of interactive applications. Recent CICS transaction server enhancements include support for web services and enterprise Java Beans, event processing, atom feeds, and RESTful interfaces. CICS Transaction Server version 4.2, which became generally available on June 24, 2011, includes support for system events, 64-bit Java, transaction tracking, and password phrases. History: CICS was preceded by an earlier, single-threaded transaction processing system, IBM MTCS. An MTCS-CICS bridge was later developed to allow these transactions to execute under CICS with no change to the original application programs. CICS was originally developed in the United States at an IBM development center in Des Plaines, Illinois, beginning in 1966 to address requirements from the public utility industry. The first CICS product was released in 1968. Named Public Utility Customer Information Control System, or PUCICS. It became clear immediately that it had applicability to many other industries, so the public utility prefix was dropped with the introduction of the first release of the CICS program product on July 8, 1969, not long after IMS Database Management System. In 1974, CICS development responsibility was shifted to the IBM Hursley site in the United Kingdom, where development work continues today. Early evolution CICS originally only supported a few IBM brand devices like the 1965 IBM 2741 Selectric typewriter-based terminal. The 1964 IBM 2260 and 1972 IBM 3270 video display terminals were widely used later. In the early days of IBM mainframes, computer software was free bundled at no extra charge with computer hardware. The OS/360 operating system and application support software like CICS were open to IBM customers long before the Open Source Software Initiative. Corporations like Standard Oil of Indiana made major contributions to CICS. The IBM Des Plaines team tried to add support for popular non-IBM terminals like the ASCII teletype Model 33 ASR, but the small low-budget software development team could not afford the $100 per month hardware to test it. IBM executives incorrectly felt that the future would be like the past with batch processing using traditional punch cards. IBM reluctantly provided only minimal funding when public utility companies, banks and credit card companies demanded a cost-effective interactive system for high-speed data access and update to customer information for their telephone operators. When CICS was delivered to Amico with teletype Model 33 ASR support, it caused the entire OS/360 operating system to crash. The majority of the CICS terminal control program and part of OS/360 had to be laboriously redesigned and rewritten by Amoco Production Company in Tulsa, Oklahoma. It was then given back to IBM for free distribution to others. In a few years, CICS generated over $60 billion in new hardware revenue for IBM, and became their most successful mainframe software product. In early 1970, a number of the original developers, including Ben Riggins, relocated to California and continued CICS development at IBM's Palo Alto Development Center. IBM executives did not recognize value in software as a revenue generation product until after federal law required software unbundling. In 1980, IBM executives failed to heed Ben Riggins' strong suggestions that IBM should provide their own IBM-based operating system and integrated circuit microprocessor chip for use in the IBM personal computer as a CICS intelligent terminal. Because of the limited capacity of even large processors of that era, every CICS installation was required to assemble the source code for all of the CICS system modules after completing a process similar to system generation, called Cics, to establish values for conditional assembly language statements. This process allowed each customer to exclude support from CICS itself for any feature they did not intend to use, such as device support for terminal types not in use. CICS owes its early popularity to its relatively efficient implementation when hardware was very expensive, its multi-threaded processing architecture, its relative simplicity for developing terminal-based real-time transaction applications, and many open-source customer contributions, including both debugging and feature enhancement. Z notation equals, part of CICS was formalized using the Z notation in the 1980s and 1990s in collaboration with the Oxford University Computing Laboratory, under the leadership of Tony Hoare. This work won a Queen's Award for Technological Achievement. CICS and the World Wide Web equals, CICS Transaction Server 2.1 introduced the capability for CICS transactions to be invoked via an HTTP request. This allowed CICS transactions to participate as servers in a POX or REST conversation. CICS Transaction Server 2.3 added new EJB tracing capabilities, and new JCICS classes, allowing the invocation of CICS services using Java. End-to-end debugging was also introduced, making it easier to debug applications, from the Java client to the CICS application. The web services support in CICS Transaction Server version 3.1 enables a CICS program to be a web service provider or requester. CICS supports a number of industry standard and specifications including SOAP version 1.1 and version 1.2, web services distributed transactions and XML encryption and signing. The CICS Web Services Assistant includes two batch processing utilities, DFHWS2LS and DFHLS2WS, which are used to map WSDL to programming language structures and vice versa, respectively. The input to DFHWS2LS is a set of control statements governing its processing and file containing WSDL for a web service to be accessed. The output is a set of language structures, each corresponding to a method in the WSDL, and a WSBIND file. This utility is intended for use by an application developer who wishes to access a web service as a client and has been provided its WSDL. In this case, the application developer populates the language structure corresponding to the method they wish to invoke, writes the structure to the DFHWS body CICS container, and executes the invoke web service application programming interface. Execution of the API is synchronous. On return, the DFHWS body contains the response from the invoked web service mapped to a language structure. The input to DFHLS2WS is a set of control statements governing its processing and file containing the language structure corresponding to the invocation parameters of a CICS application program. The output is the WSDL corresponding to the language structure, and a WSBIND file. This utility is intended for use by an application developer who wishes to expose a program's functionality as a web service. In this case, The application program is invoked when an HTTP request for its services is received by the CICS region. The application program sees the request as language structure in either a CICS container or a COM area, which one is governed by the control statements fed into DFHLS2WS. The application program performs its processing and writes the response back to the language structure it was invoked with. In either case, whether the CICS application is acting as a web services client or server, the mapping of data to and from XML is governed by the generated WSBIND file. The message body is wrapped in, and unwrapped from, a SOAP envelope by CICS Web Services plumbing code external to the application program. The connections between a web service, the WSBIND file, the WSDL, and the CICS transaction requesting or providing the services done with CICS system-level definitions and a configuration file. Also introduced with CICS TS 3.1 was the capability for CICS applications to act as HTTP clients. This allowed CICS transactions to participate as clients in a POX or REST conversation. CICS TS can be extended with additional programming features using support packs. For example, support pack CA8K introduces support for atom feeds, and support pack CA1S adds support for the PHP scripting language, using the same Java-based PHP engine as Project Zero. Often support pack introduce new technologies into CICS before they are added into the main product. For example, CA8K introduced atom feeds before it was officially integrated into the product in CICS TS 4.1. CICS family equals, although when CICS is mentioned, people usually mean CICS transaction server, the CICS family refers to a portfolio of transaction servers, connectors and CICS tools. CICS on distributed platforms a euro not mainframe as a euro is called IBM Cics series, which is available on AIX, Windows, Solaris, and HP UX operating systems. CICS is also available on other operating systems, notably IBM I and OS/2. The ZOS implementation is by far the most popular and significant. Programming programming considerations multiple user interactive transaction application programs were required to be quasi-reentrant in order to support multiple concurrent transaction threads. A software coding error in one application could block all users from the system. The modular design of CICS reentrant/reusable control programs meant that, with judicious pruning, multiple users with multiple applications could be executed on a computer with just 32K of expensive magnetic core physical memory. Considerable effort was required by CICS application programmers to make their transactions as efficient as possible. A common technique was to limit the size of individual programs to no more than 4096 bytes, or 4K, so that CICS could easily reuse the memory occupied by any program not currently in use for another program or other application storage needs. When virtual memory was added to versions OS/360 in 1972, the 4K strategy became even more important to reduce paging and thrashing unproductive resource contention overhead. The efficiency of compiled high-level COBOL and PLI language programs left much to be desired. Many CICS application programs continued to be written in assembler language, even after COBOL and PLI support became available. With 1960s and 1970s hardware resources expensive and scarce, a competitive game developed among system optimization analysts. When critical path code was identified, a code snippet was passed around from one analyst to another. Each person had to either reduce the number of bytes of code required, or reduce the number of CPU cycles required. Younger analysts learned from what more experienced mentors did. Eventually, when no one could do all, the code was considered optimized, and they moved on to other snippets. Small shops with only one analyst learned CICS optimization very slowly. Because application programs could be shared by many concurrent threads, the use of static variables embedded within a program was restricted. Unfortunately, Many of the rules were frequently broken, especially by COBOL programmers who might not understand the internals of their programs or fail to use the necessary restrictive compile time options. This resulted in non-reentrant code that was often unreliable, leading to spurious storage violations and entire CICS system crashes. The entire partition, or multiple virtual storage region, operated with the same memory protection key including the CICS kernel code. Program corruption and CICS control block corruption was a frequent cause of system downtime. A software error in one application program could overwrite the memory of one or all currently running application transactions. Locating the offending application code for complex transient timing errors could be a very difficult operating system analyst problem. These serious shortcomings persisted for multiple new releases of CICS over a period of more than 20 years. CICS application transactions were often mission-critical for public utility companies, large banks and other multi-billion-dollar financial institutions. Top-quality CICS skills were in high demand and short supply. The complex learning curve was shallow and long. Unqualified novice developers could have a major negative impact on company operations. Eventually, it became possible to provide a measure of advanced application protection by performing all testing under control of a monitoring program that also served to provide test and debug features. One such software offering was known as Oliver, which prevented application programs corrupting memory by using instruction set simulation of the application code, providing partial virtualization. Macro-level programming when CICS was first released, it only supported application transaction programs written in IBM 360 assembler. COBOL and PLI support were added years later. Because of the initial assembler orientation, requests for CICS services were made using assembler language macros. For example, the request to read a record from a file were made by a macro call to the file control program of CICS might look like this. dfhfc type equals read, dataset equals myfile, type oper equals update, etc. This gave rise to the later terminology macro-level CICS. When high-level language support was added, the macros were retained and the code was converted by a pre-compiler that expanded the macros to their COBOL or PLI call statement equivalents. Thus preparing HLL application was effectively a two-stage compiler output from the preprocessor fed into the HLL compiler as input. Command-level programming During the 1980s, IBM at Hersey produced a halfway house version of CICS that supported what became known as command-level CICS. This release still supported the older programs but introduced a new layer of execution to the new command-level application programs. A typical command-level call might look like the following. The values given in the send map set command correspond to the names used on the first dfhmsd macro and the map definition given below for the map set argument, and the dfhmsi macro for the map argument. This is pre-processed by a pre-compile batch translation stage, which converts the embedded commands into call statements to a stub subroutine. So, preparing application programs for later execution still required two stages. It was possible to write mixed-mode applications using both macro-level and command-level statements. At execution time, the command-level commands were converted back using a runtime translator, the exec interface program, to the old macro-level call, which was then executed by the mostly unchanged CICS nucleus programs. Runtime conversion The command-level only CICS introduced in the early 1990s offered some advantages over earlier versions of CICS. However, IBM also dropped support for macro-level application programs written for earlier versions. This meant that many application programs had to be converted or completely rewritten to use command-level exec commands only. By this time, there were perhaps millions of programs worldwide that had been in production for decades in many cases. Rewriting them inevitably introduced new bugs without necessarily adding new features. It was, however, possible to execute old macro-level programs using conversion software such as APT International's Command CICS. This allowed applications to take advantage of the new features of later versions of CICS while, at the same time, retaining the original unaltered code base. It is believed that there are still programs running today using this same technology. 1. New programming styles Recent CICS transaction server enhancements include support for a number of modern programming styles. CICS Transaction Server version 2.1 introduced support for enterprise Java beans. CICS Transaction Server version 2.2 supported the Software Developers Toolkit. CICS provides the same runtime container as IBM's WebSphere product family, so EJB applications are portable between CICS and WebSphere, and there is common tooling for the development and deployment of EJB applications. Transactions. A CICS transaction is a set of operations that perform a task together. Usually, the majority of transactions are relatively simple tasks such as requesting an inventory list or entering a debit or credit to an account. A primary characteristic of a transaction is that it should be atomic. On IBM System Z servers, CICS easily supports thousands of transactions per second, making it a mainstay of enterprise computing. CICS applications comprise transactions, which can be written in numerous programming languages, including COBOL, PLI, C, C++, IBM Basic Assembly Language, REXX, and Java. Each CICS program is initiated using a transaction identifier. CICS screens are usually sent as a construct called a map, a module created with basic mapping support, assembler macros, or third-party tools. CICS screens may contain text that is highlighted, has different colors, and/or blinks depending on the terminal type used. An example of how a map can be sent through COBOL is given below. The end user inputs data, which is made accessible to the program by receiving a map from CICS. For technical reasons, the arguments to some command parameters must be quoted and some must not be quoted, depending on what is being referenced. Most programmers will code out of a reference book until they get the hang, or concept of which arguments are quoted, or they'll typically use a CAN template, where they have example code that they just copy and paste, then edit to change the values. Example of BMS map code basic mapping support defines the screen format through assembler macros such as the following. This was assembled to generate both the physical map set a load module in a CICS load library and a symbolic map set a structure definition or DSECT in PLI, COBOL, assembler, etc. which was copied into the source program. Structure. In the ZOS environment, a CICS installation comprises one or more regions, spread across one or more ZOS system images. Although it processes interactive transactions, each CICS region may be started as a batch processing batch address space with standard JCL statements. It's a job that runs indefinitely. Alternatively, each CICS region may be started as a started task. Whether a batch job or a started task, CICS regions may run for days, weeks, or even months before shutting down for maintenance. Installations are divided into multiple address spaces for a wide variety of reasons, such as application separation, function separation, avoiding the workload capacity limitations of a single region, or address space. A typical installation consists of a number of distinct applications. Each application usually has its own terminal owning region, and one or more application owning regions, though other topologies are possible. For example, the AORs might not perform file I/O. Instead there would be file owning regions that performed the file I/O on behalf of transactions in the AOR. CICS Recovery Restart. Objective of Recovery Restart in CICS is to minimize and if possible eliminate damage done to online system when a failure occurs, so that system and data integrity is maintained. Under CICS, following are some of the resources which are considered recoverable. If one wishes these resources to be recoverable, then special options must be specified in relevant CICS control tables, VSAM files, intra-partition TDQ, temporary storage queue and auxiliary storage, I/O messages from to transactions in a VTAM network. CICS offers extensive recovery restart facilities for users to establish their own recovery restart capability in their CICS system. Commonly used recovery restart facilities include dynamic transaction backout, automatic transaction restart, resource recovery using system log, resource recovery using journal, system restart, extended recovery facility. Components. Each CICS region comprises one major task on which every transaction runs, although certain services such as access to DB2 data use other tasks. Within a region, transactions are cooperatively multitasked. They are expected to be well-behaved and yield the CPU rather than wait. CICS services handle this automatically. Each unique CICS task, or transaction is allocated its own dynamic memory at startup, and subsequent requests for additional memory were handled by a call to the storage control program, which is analogous to an operating system. A CICS system consists of the online nucleus, batch support programs, and applications services. Nucleus equals, the CICS nucleus consists of a number of functional modules. Task control program, storage control program, program control program, program interrupt control program, interval control program, dump control program, terminal control program, file control program, transient data control program, temporary storage control program. Support programs. In addition to the online functions, CICS has several support programs that run as batch jobs. High-level language preprocessor, command language translator, dump utility. Prints formatted dumps generated by CICS dump management. Trace utility. Formats and prints CICS trace output. Journal formatting utility. Prints a formatted dump of the CICS region in case of error. Applications services. The following components of CICS support application development. Basic mapping support provides device-independent terminal input and output. Data interchange program provides support for IBM 3770 and IBM 3790 programmable devices. 2260 compatibility allows programs written for IBM 2260 display devices to run on 3270 displays. EXEC interface program. The stub program that converts calls generated by EXEC CICS commands to calls to CICS functions. Built-in functions. Table search, phonetic conversion, field verify, field edit, bit checking, input formatting, weighted retrieval. CICS as a distributed file server. In 1986, IBM announced CICS support for the record-oriented file services defined by distributed data management architecture. This enabled programs on remote, network-connected computers to create, manage, and access files that had previously been available only within the CICS MVS and CICS VSE transaction processing environments. Pronunciation. Different countries have differing pronunciations. Within IBM it is referred to as. In the US, it is more usually pronounced by reciting each letter. In Australia, Belgium, Canada, Hong Kong, the UK and some other countries, it is pronounced. In Finland, it is pronounced Cics. In France, it is pronounced CICS. In Germany, Austria and Hungary, it is pronounced ETSEKS and, less often, EKKS. In Greece, it is pronounced Cics. In India, it is pronounced Cics. In Iran, it is pronounced Cics. In Italy, is pronounced ETE Florinix. In Poland, it is pronounced EK²X. In Portugal and Brazil, it is pronounced E6. In Russia, it is pronounced Cics. In Slovenia, it is pronounced Cics. In Spanish, it is pronounced EIX. In Sweden, it is pronounced Cics. In Israel, it is pronounced Cics. In Uganda, it is pronounced Cics. In Turkey, it is pronounced Cics. See also, IBM TX series, IBM WebSphere, IBM 2741, IBM 2260, IBM 3270, IBM OD390, OS 360, VSAM, ZTPF. References. External links, IBM CICS Family Official Website, IBM CICS White Paper, Why to Choose CICS Transaction Server for New IT Projects, CICS Official 35th Anniversary Website, CICS User Community Website for CICS-related news, announcements and discussions, Bob Yalovic CICS-focused website. Note that this site uses frames, but on high-resolution screens the left-hand frame, which contains the site index, may be hidden. Scroll right within the frame to see its content.